Well, let's start with the line segment, and we'll just pick a point, say about here, and we're going to pick up our compass, and let's measure a convenient distance on either side of that point, say here and here. And we'll label this point over here and this one over here where they intersect. Let's call this one A and this one B. And what we've done is we've found the midpoint of line segment AB, and we'll call that M. So there we have a pretty reasonable setup, and I think we can safely assume that every line segment has exactly one midpoint, by definition of midpoint, being the equal distance from either end of the segment. There's only going to be one of them. Let's take our compass again, and we'll stretch it out a convenient length, and we'll find a point above line segment AB that is equal distant from A and B. That would be right there. And we'll take our trusty straight edge and draw a line from A to that point and from B to that point. And we'll call that one C. And what we have up here then is two sides are equal to each other. And that makes this a isosceles triangle, two sides equal. Isosceles triangle. We know that A to C is the same as from B to C, or we can say the line segments are congruent to each other. And we know that point M is the midpoint. So we could say that A to M would be the same as from B to M, because that's the definition of a midpoint. Every line segment has a midpoint. Now if I was to connect C and M, I can get two triangles here. Like so. Cool. And A to M is the same as from C to M. Well, you know what? I think C to M is in both triangles, and C to M would be equal to itself. So I can say CM is congruent to CM. And that's the reflexive property of congruence, or equality if you're talking about numbers. And well, what do you suppose I've got here? I have all three sides of one triangle equal to all three sides of the other triangle. So that means that triangle AMC would be congruent to triangle BMC by the side postulate. That's pretty easy. And guess what? This angle over here and this angle over here are going to be equal to each other, or congruent, because they are corresponding parts of congruent triangles, and they are congruent. How about that? What we've got here is the base angles of an isosceles triangle have to be equal to each other. And that's kind of useful, because isosceles triangles pop up every place. And incidentally, we can also notice that angle 3 and angle 4 are going to be equal to each other. And since they add up to a straight line, then each one of these has to be 90 degrees. Isn't that interesting? We've got that one measured. Those two are 90 degrees. It has to add up to 180, and they're equal. So that's about all we know about this. Let's just take another segment for a moment over here. And we'll pick up our trusty compass, and we'll measure the length from one end to the other. And we'll swing our arc again. There we go. I missed it. There, that's better. And from the other side. And right here, the distance from there to there is the same as the distance from there to there is the distance from there to there. So if I have this connected here, I'd have an equilateral triangle. There. All three sides are equal. Well, that means that this side and this side are equal, and that makes that an isosceles triangle. And we know that the base angles of the isosceles triangle are equal to each other. So angle 1 would be congruent to angle 2 because they're base angles of an isosceles triangle. Well, likewise, this side here is the same as that side there, and that makes this an isosceles triangle. So angle 3 and angle 2 would also be equal. Angle 2 would be congruent to angle 3 because they are base angles of an isosceles triangle. That means all three of them are equal to each other. And we know that the measure of angle 1 plus the measure of angle 2 plus the measure of angle 3 must be 180 because there's three angles, interior angles of a triangle add up to 180. We know that already. And since all of these things are equal to each other, I would have angle 1 and angle 1 and angle 1 if I did substitution. That would give me three angle 1s. 3 times the measure of angle 1 must equal 180. And if I divide both sides by 3 with the division property of equality, I would end up with the measure of angle 1 must be 60. And that means that all of them must be 60, since they're all equal. Isn't that interesting? The equilateral triangle is also equiangular, and we have a way of getting 60 degrees. And this right here is 90 degrees. That also could be useful. We'll come back to that one. I think that's a pretty good little thing to discover there, don't you?